All right, welcome back to Exponents. The skills required to be able to understand the concept in this video is to understand negative exponents and how they behave, especially when the exponent gets more and more negative. Also, exponents that are zero. And of course, the easier one to understand is when the exponents are positive. All right, so for this idea, we want to evaluate, not expanded form or compact form. What is 2 to the third? What is the value? If you need to double check with the calculator, that's fine. Otherwise, pause, rewind. But either way, let's check now. What's 2 to the third? It is 8. And what's 2 to the fourth? 16. And 2 to the second, it is 4. 2 to the fifth is 32. And 2 to the 10th, see if you can get it before I write it down. It is 1024 or 1024. It is not required or necessary that you memorize these values, but rather that you recognize them as base 2. All right, so for bases that are not 0, in this course, we won't encounter 0 base. Anytime the exponent is 0, remember that if you forgot 0 or -1 exponents, please refer to episode 4 of this series. And in that episode, we talked about any exponent of 0 is 1, as long as the base is not 0. All right, and for negative exponents, we ask ourselves, what is true about negative exponents? Is the answer negative? It is not. It is the reciprocal of 2 squared. So this one's the reciprocal of 2 squared. And it'd be nice if we knew what 2 squared was, right? So 2 to the -5th is the reciprocal of 1 over 2 to the 5th. That was the idea, as the reciprocal. And it would be nice if we know what 2 to the 5th is. All right, 2 to the -3rd is the reciprocal of 2 to the 3rd. In other words, 1 over 2 to the 3rd. And next one is the reciprocal of 2 to the 1st. I will still write it in that format, but we know that it's just 1/2. That's fine if you can go straight from here to here, skipping this step. And 2 to the -6 is the reciprocal of, let me redo that fraction bar. Oh, that came out bad as well. 1 over 2 to the 6. That's the main idea. And we won't evaluate that one. Maybe we will. I don't know. It's up to you. Do you know what 1 over 2 squared is? It is 1 over 4. What's 1 over 2 to the 5th? It is 1 over 32. You can verify with the left side. 1 over 2 to the 3rd, or 2 to the -3rd is 1 over 8. And 2 to the -6, yeah, let's write it down, is 1 over 64. So I want you to think, what's happening, and associate these with y values. All right, let's look at the positive numbers. What's happening to the y value in yellow as the exponent gets larger and larger? The y values are getting larger, and not by, look, at first by a little bit, but then they get larger by a lot. And let's look at the exponents that are negative. Do those y values ever become a negative y value? And the answer is no, they become the reciprocal. But what's happening to those y values? They're getting smaller and smaller. 1 over 64 is way smaller than a half, or 1 over 8. All right, 1 over half is the largest of all of these. And if you think, what is 2 to the -10? Then it would be the reciprocal of this, 1 over 1,000, which is very, very close to 0. So it seems that the numbers are getting smaller, but closer to 0. And that's the main way we want to think about this. What is happening to the y value when the exponent, I want you to think of it as the exponent as something in green. When the exponent is positive, 2 to the positive becomes some positive y value. But remember, as the y value gets larger and larger, as the exponent gets larger and larger, the y value seems to be growing by a lot without bound. We say y value grows without bound. In mathematical terms, we say it's growing towards infinity. It will never be limited. All right, and then we have exponent of 0. That one's pretty nice. We've talked about this before. When the exponent is 0, we get a y value. Be careful, it's not 0, a y value of 1 every time, as long as the, we're going to say when the base is not 0 for this course. And then the other option is when we have negative exponents. 2 to the some negative exponent, we'll abbreviate that like this. It's the reciprocal is the reciprocal, and it's getting smaller towards 0. That's the letter C. Maybe I should erase that and make it more clear. That's how you spell reciprocal if you didn't know. So it's getting smaller. Y value. Oh, let's rewrite this in yellow. So that the yellow indicates the Y values. And we're going to use yellow for our graph below. So that makes sense. Oops, pretend you didn't see that. There we go. All right, great. We're back in business, I think. So the Y value is getting smaller. Y value gets smaller. And we say towards 0. I'm not going to write this down, but it's never negative, and it's never 0 either, okay? It just gets really small towards 0. So let's visualize this idea on a graph. And the main one we're going to use is this one because this represents a point. This right here represents the point 0, 1. And I'm going to stop color coding from here. 0 is the X value, and 1 is the Y value. So let's start with that one right there. This will become 0, 1. And again, I want you to think as the Y value is now the yellow graph, okay? We're going to make a parent. Let's try to visualize a parent graph to something like Y equals 2 to the X, 2 to the something, right? And the main thing we're going to think about is what happens when the exponent is positive. That means that the Y value is going to grow really fast without bound. And so that means that because the slope is not going to be a constant slope, oops, this is going to be a graph that curves. I hope you're thinking about that already. That's not very good. But I think that's a lot better. There we go. So it's gonna, when the exponent gets larger, it grows without bound, like really fast. You can, I hope you can see that. And then we said that when the exponent is 0, we get a 1. There's the point 0, 1. And lastly is, what happens when the exponent is negative? We take the reciprocal of those Y values, which make the Y value get really small and towards 0. So I want you to think of the equation Y equals 0. You'll see why at the moment. It's getting closer and closer and closer and closer. The Y values are getting closer and closer to 0, but will it ever reach that? It doesn't. So we have created some type of boundary for this graph. And I hope you see the equation of that line is Y equals 0. That's why I had you keep that in mind. That's going to become a boundary line, not like the axis of symmetry that we've seen before with quadratics, okay? So please don't get these confused. This is a parent function for some exponential graph, right? So let's try and highlight 3 key features. What are 3 key features of this graph that is going to allow us to transform this graph very easily in the future? 3 key features. What is something that jumps out at you immediately? I don't think that's how you spell it, but forgive me if I'm just wrong with my spelling. 3 key features. The first one that I noticed is that, and I wrote down, is that it has a y-intercept of 0, 1. And not only is, yeah, I guess it's the y-intercept. And that's because the exponent is 0. And you'll see in the, like in the next example that it doesn't matter what the base is. Whether it's 3 to the 0, we still get a 1. 4 to the 0, we still get a 1. So that's one of the first things that jumped out at me. Next thing is that it does curve. This graph has curvature. And it's upwards. It curves upwards, all right? For this particular parent function, sometimes it's going to curve downwards, but that's a transformation. And then number 3, another thing I noticed is this boundary line is bounded. This graph has a boundary. Let's write it like this. Graph has a boundary. This graph has a boundary. And what's that boundary? It is the line y equals 0. Whether the base was 3 or 4 or 5, same idea. There still would be the same boundary line. So let's show that with these 3 examples of parent functions. The first one we already did, we said, all right, we're going to take this, and I'm going to use the green color now. I really don't like the yellow one. This is 0, 1. We know that 2 to the 0 is 1. So that's what's nice about it. And we said that whenever the exponent is positive, this graph is growing without bound. And it does curve. Hopefully you can notice that. And then as the exponent is 0 and it becomes 1. But when the exponent is negative, the graph gets smaller and smaller. And it gets closer to 0, but it never reaches 0. So there's one parent graph with base 2. The next one has base 3, but let's think the same. What's 3 to the 0? It is 1. So that's what I meant. Notice how it has the same y-intercept of 0, 1. But the difference is that because the base is 3 and this one is base 2, this one's going to increase at a much faster pace. So you probably won't be able to tell this by looking at the picture. But if you were to graph these two together in a graphing calculator or graphing utility, you will see that this curves like that. And then it goes towards 0. Same idea of y equals 0 is the boundary. Let me rewrite that better. Y equals 0 is the boundary, and the equation y equals 0 is the boundary for both of these. Therefore, what do you think is going to be the boundary for y equals 5 to the x? It's still going to be y equals 0. And what is 5 to the 0? It is still a y value of 1. So 0, 1. Notice how all 3 of them go through the same. But remember that this one's just increasing at a much rapid pace than the other two. And it also reaches 0, approaches it, but never reaches it. It approaches it, I'm sorry. It gets closer and closer with some curvature. Notice how all 3 of them are curving up. So that's the main idea for the parent function. And based on this, we can easily transform them in the next few videos. So I hope that you're going to enjoy the rest of your day, and hopefully you listen to me in the next few videos, all right? This is the end for this one. Goodbye.